So last time on the limits, we found that, wait, whatever we do with the limits inside, whether it's subtract, multiply by something, add, or power, we do what it tells us to do. Because really, we're just talking about polynomials. And then algebraically, what do? We plug them in and see what happens. Because if anything strange goes on, if nothing strange goes on, the function approaches the function value most of the time. Again, unless something strange goes on. So now, let's try the same thing here. So we go ahead with direct substitution. So what happens when we plug in -1? So 4 times -1 plus 4 over -1 plus 1, and we get 0 over 0. Huh? That's something strange, isn't it? Is it 0? Because 0 over something is equal to 0. But wait, we get 0 in the denominator. So stuff over 0 is undefined, doesn't exist. Which one is it? 0 or undefined? Two different things. Number? No number. Uh-oh. That's why we have it. It's called an indeterminate form. This is just one of the indeterminate forms, and we are only going to look at two of them, the two main ones. This 0 over 0. So an indeterminate form is just that, 0 over 0. We'll put the next one down later. Means we cannot determine this limit as is. So what do? Something else. So now, really, when we're thinking about this, is what can we do in order to get rid of this factor of 0 in the denominator? So can we simplify this? Well, this function. So as x approaches -1, what's the limit? Well, let's see. We factor out the x. And what happens to the x plus 1s? Woo! Bye-bye. So the limit as x approaches -1 of 4. Done. Okay. Notice how we've seen this before. I'm going to let you ponder that for a bit and review that. Okay, so does anything strange happen here on B? Well, I don't know until I try direct substitution. So 3 squared minus 9 over 3 minus 3. By the way, this indeterminate form, this here, should go off like alarms. Warning, warning, warning. This tells you you got to do something else. Okay, so we're going to rewrite the limit. Notice, rewriting the limit doesn't eliminate this limit here. Keeps it there. Just means we're just changing the way this function looks. Well, let's see here. X squared minus 9 turns into, can be factored, x minus 3, x plus 3 over x minus 3. Can we do anything with that? Nope. And then bye-bye. So this limit, an equivalent limit. So we have an equivalent function, except one number. Guess what that number is? So now we plug it in. Use direct substitution now. 6. So this function right here looks like x plus 3, except at x equal 3. What do we have at x equal 3? Well, what happened to this factor of x minus 3? What did we do to it? It gets in an R, ends in a move. It's, remember those removables? Discontinuities? That's what we have. That's what actually is going on here. So we get, ends up being 6. What does that look like on a graph? A hole. Just like we saw the other day on the first part. So what do we do for these? Again, first start off direct substitution. What do we get? Is that 0 over 0? Is that our indeterminate form? Nope. So guess what? Nothing we can do with that. So we're basically stuck. Actually, that would be a Does not exist. Now there is a way of doing these, and I will cycle back through for that one in a little bit. Okay, so let's see here. Plug in. So 0 plus 9 squared minus 81 over 0. Well, over 0 is going to be a big indicator. Okay, there's something going on. Do we get does not exist, or do we get a 0 over 0? So 981 minus, okay. So now, the only thing we can do is simplify. So let's rewrite this. Now, because this looks factor, well, is it factorable? I'll let you go with that. But most of the time, I'm looking at this and going, okay, so x plus 9 quantities squared. Don't forget your OI. The outside's and inside, so 9x times plus 9x, that's the 18x. Then minus the 81 all over x. Still simplifying, not evaluating the limit. Changing the way this function looks. Changing the way this function looks. Still a limit of x squared plus 18x all over x. Now we could still reduce out that x. Bye-bye. One left here. So the limit as x approaches 0 of x plus 18. Direct substitution now. Plug 0 in. Notice when we plugged in the number, plugged in the as we approach, no limit anymore. Until we do that, we still have that thing there because that's what you're telling them what to do. 18. So this limit, this function here, as x goes to 0, approaches 18. How about e? Same thing. If we try direct substitution first, 0 over 0. Yeah, I set that up. So now simplifying. So notice complex number, complex fraction here. So I'm going to go ahead and do my version because it's one step. And what is my version again? Take the common denominator, so of x and 7, and multiply by it. So when I distribute 7 times 1 over x, or 7x times 1 over x, still the limit as x approaches 7. So that's 7 minus 7x times 1/7. Now, don't distribute because the idea is we're going to simplify. We're going to factor out. We're going to reduce common factors. If you multiply it, you got to turn around and factor it. Yuck. Now, the other, these look close to be the same. What's different? Oh, yeah, remember that little trick that, not trick, but the real reason that when you have subtraction in a different order, really just a factor of -1. So you can reduce that out. So this is, the limit as x approaches 7 of -1 over 7x. Now, direct substitution, -149. Now, I do want to show something like this up here. If we would have had this instead in C. If I would have had square root of x minus 5. And the reason I didn't put that up here is typo. But sometimes we get in the habit of always doing it. Got to have the 0 over 0. If you don't, no good. We will have 0 over 0 here. 20 square root of 25 minus 5, 0 over 0. Our two options for this. One is the square root's the problem with reducing. We can't reduce with that square root. So how do we get rid of square roots typically? By multiplying by the conjugate. And when we do that, we get the limit as x approaches 25. Now, conjugates Difference of two squares. So what's the square root of x squared? Square root of 5, then 5 squared. Again, the denominator, the key is we want to factor, we want to reduce, don't multiply. Oh, look. Bye-bye. So the limit as x approaches 25 of this is equivalent to 1 over the square root of x plus 5, or 1 over square root of 25 plus 5, or 1/10. That second option I talked about is really an interesting way. If you broaden your definition, what is a perfect square? In other words, is x a perfect square? In other words, okay, or x minus 25, is that a difference of two squares? Well, 25 we could see that easily. There's your difference. But what number, what thing squared gets you x? The square root of x. And then 5 for the 25. So 1 plus, 1 minus. And notice how the square root of x minus 5's, bye-bye. I know that went a little quick, but we'll see more of those as we go along. Notice how then we're back up to here to get the 1/10. So our options are multiplying by the conjugate to get rid of. That's used a lot more than this. This is more of a special case, only when that happens. Okay, we'll take a look at the remaining on other ones later.